So in this lecture, we'll be discussing polarization and complex vectors. So let's do a recap of what we learned from electromagnetic waves. And for a change, we will consider a plain monochromatic electromagnetic wave which is propagating along the y-axis. Okay. So now we know that the electric and magnetic fields have to be perpendicular to this, so they can only have x and z components. So the most general electric field is given as follows. It's E of RT is real part of a complex vector which I have shown in red, which is E1 EX cap plus E3 EZ cap times exponential of IKY minus I omega t. So the exponential factor just shows you that it's an electromagnetic wave propagating along the y direction, and the real part just takes care of getting a real electric field. Okay, so we also know that we can do the polar decomposition for complex vectors. So E1 is magnitude of E1 times e power I delta 1, and E3 equal to magnitude of E3 e power I delta 3. So these are complex numbers. So again, if E3 were 0, we have an EM wave linearly polarized along the x-axis. By that we mean that if you pick a point in space and ask how the tip of the E vector changes, it will move along a line which is along the x-axis. But more generally, if delta 1 minus delta 3, that's the difference of the phase, these two phases, is 0, pi or 2 pi, we have a linearly polarized EM wave. Okay? Now the question is, along which axis? I leave that as an exercise for you. So let us look at such examples. And so we start here. So delta 1 minus delta 3 I have chosen to be 0, but 2, the magnitudes of E1 and E3 are not equal. It's 2 times E1 equal to 3 times E3. And then we get a linearly polarized wave which is along making this angle. By the way, all these graphs are real graphs drawn using something called TIGZ, which is part of LaTeX, which is a typesetting software. So I strongly recommend that you also reproduce these graphs. Okay, so if you do this, you get a linearly polarized wave. Now consider a similar thing. Keep delta 1 minus delta 3. That means they have to be pi by 2. And the magnitude of E1 and magnitude of E3 are equal. Then we get circularly polarized light. Again, I leave it to you as an exercise to check if this is left circularly polarized, and also do one more thing, which is to change this, add pi to this, so it will be 1.5 pi, and ask, does it become the other polarized light? So you need to check that, and so please do that. So these are two. So this is linearly polarized by light, and this is circularly polarized light. Now we can consider more general situations. Now we keep delta 1 minus delta 3 to be pi by 2 like before. But now the magnitudes are no longer equal. It's the same as here. 2 E1 equal to 2 E3, 3 E3. So we get an ellipse with semi-major and semi-minor axis along x and z axis. And now what we do is we keep the magnitude ratios the same, but now we start playing around with it. So delta 1 minus delta 3 here is 0.7 pi. We get an ellipse which is tilted to the left, and delta 1 minus delta 3 equal to minus 0.2 pi. It goes something tilted to the right. So all these are elliptically polarized light, and this is the generic case. So the key point, remember, is that the polarization data is a complex vector. So it's a two-dimensional vector because it's only along E, X and Ez, but its components are complex valued. Okay, and this just says that the ky means it's propagating on the y direction, and omega is the angular frequency. So this complex vector, this symbol is the calligraphic E. So the cal E encodes the polarization data, and since its components are complex, we call it a complex vector. Okay. Then we know a few more facts which we had worked out. If you did the time average of the energy density in the EM wave, we saw that it was proportional to the length of this complex vector, but this length involved complex conjugation. So it's dot product in the usual sense, but it's epsilon, cal epsilon star, complex conjugation, dot, cal epsilon. Okay. But since our vectors are complex, we have the freedom to choose basis vectors that are complex as well. So one example would be to choose E plus minus to be 1 by square root 2 Ez plus or minus IEX, and the reason I choose x z before x here is because we want a right-handed coordinate system. So z, x, y form a right-handed triad. So rather than x, z and y, that would be left-handed. So just keeping that convention, we have chosen it this way. So but note that if you have this complex basis, now you need to put complex conjugation not just in in the vector. You need to also do complex conjugation of the basis vectors. So you can check. Again, nice exercise. EI star dot EJ is equal to delta IJ for IJ equal to plus and minus. So this is the orthonormality of the basis. So because we are in complex numbers, you can see that we need to use complex conjugation. And also we can see that if we stick to reals, complex conjugate of a real number is itself. So this reduces to the usual case if we had real vectors. So it's a nice simple-minded generalization of something we already know. Okay. So now what we can do is, since we have a complex basis, we can go ahead and use this to expand the most general elliptically polarized electric field. Say now you just get coefficients E plus and E minus, and again E plus and E minus are nothing but complex numbers. And by just some trivial algebra, going back to the previous page, equating these two expressions, this one with this one, it's trivial algebra to show that E plus is E3 plus E1 upon root 2, and E minus E3 minus E1 upon root 2 I here is square root of minus 1. So when E plus is 0 or E minus is 0, we obtain circularly polarized light, and I leave it as an exercise for you to figure out which one is left circular polarization and which one is right circular polarization. And at this point I must tell you that every book has its own definition. So there are two possible definitions, and I think there is no uniformity in that. So don't lose sleep over what is left or right circularly polarized. Pick a definition and work out the identification. So this is a fun exercise. So one conclusion we can draw from here is, if when E plus and E minus is non-zero, we get an arbitrary polarization, and that can be obtained not just as we saw before, but now as a complex linear combination of left and right circularly polarized. So there is nothing special about the linear basis that we considered first. Okay. So at this point, we have seen how the fact that we have complex vectors means we can choose basis vectors which are complex value objects, and only thing we need to do is to be careful to include the complex conjugation into the inner product or dot product of vectors. Okay. So now we are ready to play some fun games with polarizers, and I will do some simple examples, but I will let you play with more complicated ones on your own. Okay. So first thing is, what are polarizers? So these are optical filters, and there are many ways of constructing them. I suggest you look up on the net, but for us, we just want to know what they do. So what they do is they take unpolarized or elliptically polarized light as input and produce polarized light as output. So linear polarizers produce linearly polarized light, while circular polarizers produce circularly polarized light. Okay. So for the rest of our discussion, we will stick to linear polarizers. Not that we couldn't have worked with circular ones, but for ease of presentation, we'll stick to linear polarizers. So here's what, and we saw that we have a complex vector cal E, which parameterizes the most general elliptically polarized light moving along the y direction. Okay, so we'll keep that y direction fixed, that's the direction of propagation. We'll also keep omega fixed, that means it's monochromatic. Okay, we do nothing to all those things. And if you send in this light through a Z polarizer or Z polarizer, what it does is it projects only the component along the Z axis. So obviously the intensity and the energy density, etc., goes down, but that is not important at this point. It is relevant, but not important. So what is important is that it projects out the Z component, and we get a vector. We get a complex vector, of course, but there's a special complex vector with only a component along Z direction. And here is the deal. You can just take this polarizer and rotate it about the y-axis by, say, pi by 2 radians or 90 degrees, and then this Z polarizer becomes an X polarizer. And what does it do? It does something simple. It takes a general guy, and output is now E1 is only the component of this thing along the X direction, and that is what we see out here. Okay, so the output is still a complex vector, but the component in the orthogonal direction, which is Ez, has been projected out. Okay, so this is what these two things do. Now we understand what a polarizer is, but we would like to ask, the next question is, what if we had rotated by an angle theta? Okay, so that's not so hard. We just define a vector n cap, which is the, if you take, let's say you took a z-axis and rotated by theta, it will give you, the z-axis will become this vector n cap, and simple trigonometry will tell you that that's cosine theta Ez cap plus sine theta Ex cap. Okay, n hat is of course perpendicular to the y direction. Okay, so if you rotate a polarizer, then the output will be the projection of the complex vector along n cap with magnitude epsilon cal epsilon dot n cap. So you just do this, and you see it will be E3 cos theta plus E1 sin theta. So you remember E was in this form, in this form. So if you dot it with n cap, it will be n cap was what, cosine theta Ez cap, so that you will get E3 cosine theta, and the dot of the other part of it will give you E1 sin theta, and that's what we have written here. Okay, so so let's call this object a theta polarizer. So theta equal to 0 is a Z polarizer, and theta equal to pi by 2 is an X polarizer. So you just get, you send in cal epsilon, general elliptically polarized guy, and lo and behold, the output is E3 cap cosine theta plus E1 sin theta, that's the magnitude, times n cap, because it's polarized. What comes out is polarized along the n cap direction. Okay, so now questions to you, for you to think about is what happens. I said theta equal to 0 is basically the X polarizer. What about theta equal to pi? Similarly, what about theta equal to 3 pi by 2? Okay, leave it as an exercise for you to play with it and see what you get on the output, and the answer is interesting. Now we can play games, and we consider sequential polarization. And so what we are doing here is taking a general elliptically polarized guy and sending it through a Z polarizer, and again sending it through a Z polarizer. These two are parallel polarizers. So we already saw that the output of this would be E3 Ez cap, but the second polarizer does nothing. So because there is nothing to project out, it's already aligned up with this, and so the answer. So the second Z polarizer does nothing. You get the same output that you would have got out here. Okay. So now let's change things up a bit. Let us send a second combination. Now the second guy I change. Here it was a Z polarizer. I make it an X polarizer. But now we know that X is orthogonal to Z, and so if you dot E3 dot E3 Ez cap with Ex cap, you get 0. So you get nothing. So if you are looking and think of this as light, you will see a black patch. You will see nothing. Okay. So these two guys are quite interesting, and shows you how polarizers can be used to tweak things. So you can think of this first single polarizer as blocking out. Sometimes you want to remove some component, and that's what it does. Now we can do an interesting modification to this. So here we have a Z polarizer and an X polarizer. Now suppose I inserted a third polarizer, but now between these two guys, remember we got 0 here, And so now what we have is a Z polarizer, and I pick a particular value of theta, say it's pi by 4 polarizer, and you get output which is X, and then the next one is the X polarizer. The question is, what is the output? Okay, so we have to handle this sequentially. So let's just call the output here as epsilon, cal epsilon 1, cal epsilon 2, and cal epsilon 3. So we want to really know what cal epsilon 3 should be. But it's not hard. We can go do it only step by step. And in this case, just for pi by 2, n hat is just Ez cap plus Ex cap upon root 2. Okay, n hat for this pi by 4 polarizer. Just remember that. Okay, so we first output here is just dotted, and we saw that this was E3Z. But now you got to dot this with n cap of pi by 4, and that will give you a E3 upon root 2 times n cap, which is another root 2. So the two root 2's become a 2. So you can see it is something along Ez cap plus Ex cap. Now we do it, pass it through an X polarizer, and that is just dotting with Ex cap, and so that will just pick out this component, and that's just E3 by 2 along the Ex cap direction. So what we see here is a sequence here. Here is no longer 0, 1, because what we have done is to rotate this Z polarized guy into something along the pi by 4 direction. Okay, so these games you can play around. I would suggest you put other things. You could do pi by 3, ask what will you get, and so on and so forth. Again, these are games you can play. But I will finish this lecture by looking at matrix representation of linear polarizers. And so to understand this, what we do is we associate a column vector. So epsilon, cal epsilon is your complex vector. So you can see that I can write E3 and E1. These are the components. First entry is a component along the Z direction. Second entry is a component along the X direction. So we can just write this. And now we can ask, if we pass this through a theta polarizer, what will be the output? And we can just go ahead and write out the matrix representation of, rather the column vector representation of this vector. And if you just go ahead and do that, we get E3 cosine square theta plus E1 sine theta cosine theta. Similarly, you get, this should be E3 sine theta cosine theta plus E1 sine square theta. Okay, so this is what we get. But now we can write this as a matrix, which I indicate in red, acting on the original vector. Okay, and let's just call this vector P of theta. So P of theta is a 2 by 2 matrix, which tells you what is the output if you passed a general polarization through a filter to a theta polarization. Okay, so the matrix P of Z in red captures all the details of the theta polarizer. So if you give me a polarizer, then I can associate a matrix with this. So now the question to ask is, what about the cases when you have sequences of polarizers like here? Okay, so first exercise for you, of course, is to write out the matrices for each of these polarizers, and let's just call this one P1, P2, and P3. And the exercise for you is to check that the final answer that you get here can be written as the matrix product of the various matrices. So question to you is, in this case, is it P1 multiplied by P2 multiplied by P3, or is it the other way around? P3 multiplied by P2 multiplied by P1. Again, please check that. Okay, and so that concludes what I wanted to say about matrix representation of linear polarizers. So you know what a linear polarizer is, you know how to represent it as a matrix. And so let us finish with a summary. So now I will write things slightly more abstract. Remember, all our discussion was based on assuming K was along the Y direction. Now I don't assume that. I just say that there is an arbitrary vector K, and what the complex vector cal epsilon satisfies cal epsilon dot K equal to 0, and the key is that key is that if epsilon 1 and epsilon 2 satisfy star, then so does any complex linear combination a1 epsilon 1 plus a2 epsilon 2, where a1 and a2 are any two complex numbers. The space of complex vectors is two-dimensional in the sense that we have two basis vectors and we need to specify two complex numbers. And it's up to us as to how we represent them. For instance, if we have a fixed basis, I can just write it as a column vector like I did here, and these two columns, if you know the rules, we can go back and forth. This arrow is not one way, we can go backwards as well. Okay, and the other feature is that the energy density of a wave is proportional to the norm or length of the complex vector. So that if you remember, it will be this thing divided by 2 epsilon naught. Okay, and polarizers or sequences of polarizers can be represented as 2 by 2 matrices acting on the complex vector epsilon, which is represented as a column. So amazingly, the properties that I just described in the summary appear in the context of linear vector spaces, and this is what we will study next.